Okay, so good morning, everybody. Again, a rainy, stormy day outside. Nice and cozy in here. Let me remind you what we did last time concerning derivatives. So this was the definition of the derivative at the point x0, providing, of course, that this limit exists. So we wrote two different ways of expressing it, and they're completely equivalent, and we're going to be using both of them. And we had some theorems. And I wrote the formulas, not the entire theorems, just the formulas that are not completely trivial to remember, but you have to remember them. So this is the derivative of a product, the derivative of a quotient, providing, of course, that g is not 0. This is the chain rule. If you have a composition, f of g of x, and you want to take the derivative, you take the derivative of f at g of x times f prime, times g prime. I confused I think we wrote it the other way last time. We had g of f of x. It doesn't matter, of course, but this is what you get. So this is what we call the inner derivative, and this thing is called the chain rule. And finally, the derivative of an inverse function. If you want to take the derivative of f inverse at the point y, that's 1 over the derivative of f at the point x, where y is f of x. So it's not that these are two unrelated variables. They're related via the inverse function. Okay, so I want to do a couple more remarks and examples, and then move on to some more theorems. So first of all, another example. Suppose we want to take, so this is example 1 for today. Suppose we have the function f of x equals x to the power alpha, where alpha here is a parameter, any real parameter, and the domain is only for positive x's. And we want to take the derivative of this. So we're going to do a very standard sort of, you can call it a trick. It's not really a trick. It's just a standard procedure. We're going to define a new function, call it g of x. G of x is going to be ln of f of x. Define. Now, g is a new function. G is the composition of these two functions. Do you agree? So we can take the derivative of g using what? The chain rule. So the derivative of g at x is the derivative of the outer function, ln. What's the derivative of ln? 1 over. But it's not going to be 1 over x. It's going to be 1 over the argument of ln. So 1 over f of x. Times the inner derivative. What's the inner derivative? The derivative of f, so it's f prime of x. So this is simply using the chain rule. Good? Okay, now let's do the same thing. So on the other hand, I can take the derivative of g in another way, because what is g? G is ln of f of x, but f of x is not something mysterious. F of x is this function. So g of x is ln of x to the power alpha. And we know from rules of logarithms that this alpha can bounce down here, right? So this is the same as alpha ln of x. Do you all agree? Okay, so what is g prime? So therefore, the derivative of g is the derivative of this thing. So alpha is just a number, a scalar. So it's alpha times the derivative of ln, which is 1 over x. So I took the derivative of g in two separate ways. But it's, of course, the same function. The answers have to be the same. So this has to equal this. Let's write that and see what we get. Let me erase the words chain rule here and clear some more board so we don't have to take another one. So this is equal to this. So therefore, we can say that f prime x divided by f of x, but I know what f of x is. It's x to the alpha. So that's rewriting this. That has to be equal what we got here, alpha over x. Right? Good? Good. And now what do we get? We get that f prime of x, which is what we were looking for. We were trying to take the derivative of that function. So f prime of x is alpha times x to the alpha divided by x, so times x to the alpha minus 1. And this is the conclusion. Note that I assume you knew this for natural numbers. You knew that the derivative of x squared was 2x, and the derivative of x cubed was 3x squared, right? But in fact, this works for any real alpha. Okay? So that's this example using the chain rule. And this is standard because of this phenomenon. Many times when we have an exponent, in various situations, not just for taking derivatives, when we have an exponent, it's a good idea to take its logarithm, which allows you to pull down the exponent as a coefficient, and continue from there whatever you're doing. Okay, so this is kind of a standard tool that should be in your toolbox. Ooh, I can use it in various contexts. Okay. One more remark that I want to make. So, remark. Remember that when we wrote the... Maybe I'll make this remark on that board. Let's go back to this board a second. And let me erase these things. You have them already. Let me erase this thing too. And the remark concerns the chain rule. Remark. So remember that when we said that this is the notation for the derivative, we also gave a different notation, which we said was due to Leibniz. Do you remember what it was? Right. Well, dy over dx, or if we called it f, so a different notation would be df over dx at x0. This is just different notation for the same thing. Okay? Now, this notation is just as useful and just as common. In fact, you'll see that it's used very often in the multivariable context, in Calculus 2. In this class, I'm mostly going to use this notation just because it's shorter to write. So it's easier. It's just a little prime. But I want to show you that this notation is, in fact, very wise. This is just notation. This notation hides, in the notation itself, some deep truths. For example, this theorem. Okay? So this is a theorem, the chain rule. You have to prove it. We didn't prove it. And the proof is not that straightforward. You have to work a bit to prove this. But I want to rewrite this using this notation. So what do we have here? We have f of g of x, and we want to take the derivative of f with respect to the inner variable, with respect to x, right? That's what we're doing. So that's going to be written df to dx. And this theorem says that that's the same as taking the derivative of f, but not with respect to x, with respect to everything inside, with respect to g. So this would be written in this notation, df to dg, thinking of g as the variable of f, times this inner derivative is dg to dx. So writing this theorem in Leibniz notation, it's just notation. This doesn't prove anything. This is not a proof. But the notation is so smart that it kind of suggests, hey, cancel out this thing, and there you have it. That's the proof, right? It's nonsense. You can't cancel out this because it's just notation. But this shows you how the notation is wise. And one can write the formula we had down here for the derivative of the inverse function. Okay? So what, do you remember what it was? So suppose y is a function of x. So it says that the derivative of, so y is a function of x. The inverse function is writing x as a function of y, right? And the theorem in Leibniz notation would be dx to dy is 1 over dy to dx. Do you agree? Again, seems like just true, but it's not a proof. It's just good notation. So that's a remark. So remark, this is a chain rule in Leibniz. Leibniz. Is this how you write it? I even don't remember. Notation. Am I missing? There's a T here? Nah, I'm just kidding. Where? Before the Z?
Yeah.
I'm not sure. That would be in English. I'm not sure, but... Okay. I apologize to Leibniz if I misspelled his name. Maybe the I and the E are I'm sorry, I should know better, but anyway, that's this remark. Okay. So now we know how to take derivatives, and that's good. I want to write down, just take this a step further. So when you have a function, okay, so let's put a title, higher order derivatives. So when you have a function f, if the function is differentiable on an interval, for example, then you have the derivative function. So you can write f prime. F prime is defined pointwise. At any x0, it's defined using that limit definition, right? But once you do it for every x0, you get the derivative function. You get a new function, right? The derivative of x squared is the function 2x. Do you agree? You can take the derivative of this function too, right? And the notation would be f prime prime. So this is called the second derivative of f, and it's just the derivative of the derivative. Okay, so I'm not going to write too many words. Is it clear what this is? Okay. You can still do it for 3. You can do it for 4, but this notation is starting to get a bit, doesn't look right. Right? We're not going to put f in 17 primes when you want the 17th derivative. Okay? So the notation usually used for 4 and above, sometimes also for 3 and above, is f n x. But writing it like this would mean that it's f to the power n, so that's not good. So the notation is this. This is the notation for the nth derivative of f. Okay? Nth derivative of f. That's the notation used. Usually for 1 and 2, we don't use this. We rather just use the primes. For 3 and above, it's customary to use that. Okay? The theorem for higher order derivatives is the following. If f and g are differentiable n times, meaning they have nth order derivatives, then if you take a constant times f and take the nth derivative, you get the constant times the nth derivative. If you take the sum of f plus g and you take the nth derivative, you get the nth derivative of f plus the nth derivative of g. And things get interesting when you go to the product. You should expect, of course, that it's not going to be just the product of the derivatives, right? Because even for n equals 1, we know that's not true. Right? Even for n equals 1, we get f prime g plus g prime f, right? So for higher n's, it gets messy. There are a lot of terms. And if you think about it for a moment, what would be the second derivative of this product? It would be the derivative of f prime g plus g prime f, right? That's the second derivative of fg. And each of these two factors, f prime g and g prime f, is itself a product. So when you take the derivative of that, you're going to have two factors. Do you see that? Okay? So you can try writing the first, the second, the third derivatives and see what you get. You're going to get more and more terms as you get higher in the order. And the ultimate formula for a general n is the following. It's the sum k equals 0 to n. Let me erase this and put a line here. It's the sum k equals 0 to n, n over k, f kth derivative, g n minus kth derivative. Right. It's very similar to the binomial expression, except it's for derivatives. Does everybody know what this is? No? So let me tell you what this is. This is notation. This thing is notation for n over k is just notation for n factorial divided by k factorial times n minus k factorial. Do you all know what factorials are? Right? N factorial is n times n minus 1 times n minus 2 times n minus 3 all the way down to times 3 times 2 times 1. So this is just notation for this thing. And it has a lot of uses in mathematics. It's closely related to some issues in combinatorics. But that's besides what we're doing here today. So I'm not going to get into that. For us, it's just notation for this thing. And this formula highly resembles the binomial formula, if you know what that is. If you don't worry about it right now. Maybe you'll discuss it in the tutorial. So let's do an example of using this, just a short example. So here's an example. By the way, this is called Leibniz formula. That's the name of, so this is called Leibniz. Now I don't know how to spell it. And now I'm not even Leibniz, hopefully. Formula. Okay, so let's do an example. So suppose I want to take, example 2 for today. Suppose I want to take the function x squared, multiply it by e to the x, and then take the 9th derivative of that thing. Okay? It's not brutal, it's easy. Let's do it. So I'm just going to look at that formula, which is on the other board, and how many expressions do we expect? How many terms are there going to be? Well, this formula here, look at the formula again. K goes from 0 to n. So there are from 0 to 9, so there should be 10 expressions, 10 terms in the sum, right? So I'm going to calculate n over k, where n is always, Let me write it. Let's write this. So it's sum k equals 0 to 9 x squared kth derivative times e to the x n minus kth derivative, and I forgot the coefficient, 9 over k. That's just plugging in everything into the formula. Okay? So let's spell this out, see what we get. So we start from k equals 0. For k equals 0, we get 9 over 0 times x squared, the 0th derivative. The 0th derivative, by definition, is just the function itself. So x squared times, oh, this is not n, this is 9, times the 9 minus 0, so the 9th derivative of e to the x. Right. E to the x, its derivative is e to the x. Therefore, its second derivative is e to the x. Therefore, all its derivatives are just e to the x. Right? So here we have e to the x. Do you agree? Plus, and now I have to plug in k equals 1. So for k equals 1, I get 9 over 1. The first derivative of x squared, which is 2x, times the 8th derivative of e to the x, but that's still just e to the x, plus 9 over 2, the derivative of this. What's the derivative of this? 2. And the 7th derivative of e to the x, which is still e to the x. What about the remaining 7 terms?
0.
They're dead. Because the derivative of f, the third derivative of this thing, is already the first derivative of 2, which is 0. So all the remaining terms contribute nothing. Do you see that? Okay? So that's it. That's all we get. Okay? And now we can write what, okay, so 9 over 0 is 9 factorial over 0 factorial, which by definition is 1, and minus 0 factorial. So, right? N factorial over k factorial and minus k factorial. So here it's just 1. The 9 factorials cancel. So we get x squared e to the x. 9 over 1 is 9. Okay? So we get 9 times 2, so plus 18 x e to the x. And 9 over 2 is 9 factorial over 2 factorial, 7 factorial. The 7 factorial and the 9 factorial cancel out, leaving just 9 over 8, divided by 2, so it's 9 times 4. So it's what? 36. So, oh, times this 2. So it's 72 e to the x. If that was too quick for you, just write it down, and you'll see it, okay? And that's it. That's the 9th derivative of this function. How can you, oh, you can pull out an e to the x. You could. It doesn't really matter. You could. You could.
We don't know that e to the x, when we take the derivative, it's e to the x.
E to the x, the derivative of e to the x is e to the x. We used it all along.
No, we didn't do that before.
Yes, we did. Well, we called it e to the y, because we did it as the inverse function of ln of x, and we did that last time. Okay?
I have a question.
Yep.
From the properties that we have when it's factorial 1, just can I say that the n factorial is going to be, when it's a multiplication of two functions, is, you follow?
No, I'm not sure I'm following.
I just want to compare between the first derivative and the nth derivative.
Okay, so compare between the first derivative and the nth derivative. If n is 1, so you get your sum from 0 to 1. So there are going to be 2 terms, right?
Okay.
The first term is going to be n over 0, which we just said is 1, times f first derivative, sorry, f 0th derivative, which is f, times g 1 minus 0, first derivative. So you get f g prime. Plus, now you plug in k equals 1, right? So you get 1 over 1, which is again 1, And now you get f first derivative, f prime, g zeroth derivative. So you get f prime g plus g prime f. You get precisely the formula for the product when n equals 1. Precisely. Okay. So this is all I'm going to say about these things. I'm going to give you one, if I find it. Have to find it if I want to give you to try it. Yeah. So try this. So this will be example 3.
Is n factorial 1?
N factorial is n times n minus 1 times n minus 0 factorial is 1 by definition. So try this. Try this. You can't, there's no formula, at least not that I know of, for an nth derivative of a quotient. Okay? But you can write this as a product. X squared times 1 over 1 minus x. Right? And then you can use this Leibniz formula and find the nth derivative just like we did here. It's going to be, n is general. Okay, I'm not telling you what n is for any n. And you have to do this carefully. There are some, no, homework. I'm not going to discuss it now. So please try it, okay? Try it. Try it at home. I want to stop this discussion here, okay? And I want to move on to the fundamental theorems of differentiable calculus, okay? Which are not going to surprise you because we met them already. So the Leibniz rule? How do you derive the Leibniz rule? Oh, you can do it. That's what I said. Try it for n equals 2, see what you get. Do it for n equals 3, see what you get. And you're going to see with your own eyes that the formula just kind of reveals itself. You see that there's... of course you have to prove it, okay? But proving it would be kind of an induction argument, okay? This is not hard. Once you know the formula for the product, for the derivative for the first derivative of a product, and that we even proved. Okay, so this is not hard. You can do it. Okay, so what I want to do now is discuss the theorems. Okay, so the fundamental theorems. Theorems of differentiable calculus. I don't want to write the word fundamental because there's a very specific theorem called the fundamental theorem of calculus. And we'll get to that, but that involves also integrals. We'll get to that. So these are the basic theorems of just differentiable calculus. And here we go. I'm going to do it pretty quickly because we discussed these. These are precisely the theorems that we had in the introduction. Okay? But now we're not going to just wave our hands at everything and say, well, continuity is something you can draw without lifting the marker off the board. And differentiability just means smooth, having no cusps. Remember, that's how we discuss things in the introduction. Now we can do it more formally, and I want to do it more formally, and I actually want to prove these theorems. So the first theorem is Fermat's theorem. So this is going to be 1. And it says the following. Let f be defined on some open interval AB, and let x0 be a maximum or a minimum of f at which f is differentiable. Okay, so I'm assuming x0 is a minimum or a maximum, but I'm also assuming that f is differentiable at that point. That means that f prime exists. Then, what is the then? Right. The derivative at that point is 0. We argued this in terms of the picture. We said, well, here's a short reminder of the picture. We said, if you have a function and it has, let's say, a maximum, and suppose the maximum is at some point, so this is f, and suppose the maximum is at some point here. Here's the maximum. So this is x0. Well, the tangent line at that point has to be horizontal, which means that the derivative, which is the slope of the tangent line, is 0. Do you agree intuitively to this theorem? Yes? Okay, but I want to prove it now. I want to formally prove this theorem. And the formal proof of this theorem will actually be what's called epsilon neighborhood of the definitions. So I'm not going to pull any bunnies out of my hat, just the definitions. No magic. So, proof of Fermat's theorem. Proof. So what do we know? We know that f is differentiable at x0. What does it mean to be differentiable at x0? It means that that limit that defines the derivative exists. That's all. Right? No. Being differentiable, by definition, what it means is that the limit defining the derivative exists. It was a theorem that implies that the function is also continuous at x0, but that was a theorem. We proved it. Okay. So proof, f prime at x0 exists. And it equals, let's write it using the x goes to x0 notation, it equals the limit, x goes to x0, f of x minus f of x0 divided by x minus x0. That's the data. Okay, we know that this limit exists. Now, when a limit exists, it means that it's equal to both one-sided limits. Do you agree? That they exist and are equal. So I can write that this equals the limit as x goes to x0 plus f of x minus f of x0 divided by x minus x0. And it also equals the limit as x goes to x0 minus of f of x minus f of x0 divided by x minus x0. Whenever a limit exists, both one-sided limits exist and are equal to that limit. Okay. Now, let's consider only x's greater than x0. X is to the right of x0. In this situation, do you agree that x minus x0 is positive? If x is greater than x0, then x minus x0 is positive. Do you agree? Okay, I have to go a bit back. So the theorem says it can be either a maximum point or a minimum point. The proofs are going to be astonishingly similar. So we're not going to prove both. We're going to prove one of them. And what's the word? What's the terminology we use? Right, without loss of generality. So I'm going to add here, without loss of generality, x0 is going to be, let's say, what did I use? A maximum. Okay? Okay. So when x is greater than x0, when you're looking at x's to the right of x0, this holds. What about f of x minus f of x0? If x0 is a maximum, then f of x0 is greater than or equal to f of x for any x. Do you agree? That's the definition of x0 being a maximum. So this is greater than or equal to this. So this minus this is less than or equal to 0. Good? Everybody? Okay. So what can we conclude? So from this we can conclude that for any x greater than x0, the quotient f of x minus f of x0 divided by x minus x0, the denominator is positive, the numerator is non-positive, so this whole thing is non-positive. Do you agree? Good? Okay. Now, this implies that when you take the limit as x approaches x0, coming only on x is greater than x0, so x approaches x0 from the right, it's a limit of a function which is non-positive. What's the limit going to be? It's also going to be non-positive. Do you agree? There's no way that a function which is always non-positive is suddenly going to have a limit which is negative. Right? Do you agree? Okay. We proved it. In fact, we proved it. That if you have a limit that then close enough to... If you have a limit... No, we proved this as is, but maybe not with... just with f. If you have a function, okay, and think of this entire expression as just a function, okay? It's made up of stuff, but think of it as just a function. This function, for any x greater than x0, the value is non-positive. As you approach x0, the limit can't suddenly be something negative, or something positive, right? If the function is always under the x, the limit suddenly... Right? That's the whole concept of a limit. You get closer, right? Do you see that? I think we proved it formally at one point or another. Okay? What about x's that are smaller than x0? X minus x0 is now negative, right? What about this difference, f of x minus f of x0? Right, this remains the same because we're still under the assumption that f of x0 is a maximum. So it doesn't matter to which side of x0 x lies, f of x0 is going to be greater than or equal to it. Right? So in this case we get, so here we got this, here we get that f of x minus f of x0 divided by x minus x0 is always non-negative, right? We take something non-positive and divide it by something negative, we get something non-negative. And this implies that the same would happen in the limit. It doesn't imply that the limit exists, but if it exists, it would be the same, and we know that it exists because we know that these one-sided limits exist. So we get f of x minus f of x0 divided by x minus x0, and now we get that this is non-negative. Do you agree? But that's it. We found on the one hand that the limit when you approach from the right is less than or equal to 0. The limit when you approach from the left is greater to or equal to 0, but they're equal. Something greater than or equal to 0 and less than or equal to 0 can be the same if and only if they're what? 0. So from here and here we can conclude so call this fact star, call this fact star star, and let's finish the proof here. Star plus star star imply that f prime at x0 is 0. And that's what we wanted to prove. So this is what I mean when I say that the proof is in an epsilon neighborhood of the definitions. I really just used purely the definition itself. I didn't even resort to the fact that f is continuous at x0 or any derivatives of products or whatever. Nothing. Just the definition. Okay? Good? Okay. I want to remind you, we said this in the introduction, so let's look back at the theorem itself. I want to remind you that the use of this theorem is something you've been doing for a long time, since high school. When you're studying functions and you want to find their maxima and minima, what do? You said, okay, let's find the derivative, set it equal to 0, and solve. Find which points satisfy this. Points that satisfy this are candidates for being minimum and maximum, because any minimum or maximum would satisfy this. Everybody knows what I'm talking about, right? Good. And it's not, we also said that, it's not an if and only if statement. So a minimum or a maximum can hide among points where the function, for example, is not even differentiable, right? For example, at a cusp. You could have a maximum at a cusp, and this process won't find it because f is not differentiable at a cusp, right? Think of, for example, the absolute value of x. So let's write examples to think about, just since they express these things to remember, that this is not an if and only if statement. You know this stuff, but examples. Absolute value of x has a minimum at x equals 0, right? Although, of course, this function is not differentiable there, so it's not going to, Fermat is not going to pick up that minimum, right? The function x cubed does not have a minimum, or a minimum or a maximum at x equals 0. Why am I saying this? Because this is a situation where the derivative is 0, right? X cubed looks like this. The derivative at 0 of x cubed is 0, right? The derivative is 3x squared, and at 0 it's 0. So the tangent line, maybe this is not an accurate drawing, the tangent line is the x-axis, but it's not a minimum or a maximum. So it's that theorem you have to use with caution. It doesn't pick up all the minimum and maximum points, and it could pick up points which are not minima or maxima. Okay? So you have to be careful when you use it. Yes?
So could we just say that the opposite, like the vice versa, does not imply, like that if the
Well,
derivative is
two vice versas are not true. That's what I'm saying here. If the derivative is 0, it doesn't necessarily imply that it's a minima or a maxima. Okay? And if it is a minimum, it doesn't necessarily satisfy that the derivative is 0. It could be a cusp, it could be an endpoint of the interval, it can be many things. Okay, so remember these things when you study this. Yes?
Actually, when we are applying this theorem the other way around, don't we say we're looking for extreme points and not for maximum?
Extreme points are.
In that case, it would be, I don't know, we call it like subtle, I don't know.
We use the theorem to find extreme points. Extreme points are, by definition, minima and maxima, just a family name for both. And in seeking them, points like this, which we will call a bit later inflection points, are picked up, but they're not extreme points. This is not an extreme point of x cubed. Okay, that's the statement. Okay? Okay. Good. The next theorem in this line of theorems was Rolle's theorem. So, Rolle, French dude, said the following. If f is continuous on the closed interval AB and differentiable on the open interval AB, these were the requirements, and the value at the endpoint A coincides with the value at the endpoint B, then there exists a C in the interval such that the derivative at C equals 0. That was Rolle's theorem. We had a picture for it. Let me remind you of the picture. Here's A, here's B. The value at A is the same as the value at B. So either the function is the constant function, in which case for any point C the derivative is 0, or it goes up, but then it must come down because it has to get to here. Okay, this is just the intuition. This is not a formal proof. So it can come up, it can come down, but in any event there are going to be these points where the derivative is 0, where the tangent line is horizontal. Okay? I'm not spending too much time on the picture because we did this. We discussed this. Okay? I want to prove this theorem formally. Proof.
What is the difference in the Weierstrass theorem?
This is a statement about derivatives.
No, I mean,
I don't know what that
Okay?
is.
The Weierstrass theorem said, okay, if you have a continuous function, it has nothing to do with differentiability. It can be completely cuspy. And in fact, we're not going to spend time on pathologies, but one can construct a function that's continuous and not differentiable at any point, and all kinds of weird things like that. Okay? But even if a function has a cusp, if it's continuous, it's bounded, has a minimum, has a maximum. Continuous on a closed interval. Here, this is a statement about derivatives. Proof. In contrast to the proof of Fermat's theorem, this theorem, the proof, is going to be using previous theorems. Okay? And I'm going to start by writing it, and then I'm going to discuss it. Okay? So, what I'm going to try to do in the proof is just like the intuition. I'm going to say, okay, it has to have a minimum or a maximum. Therefore, by Fermat's theorem, the derivative at that minimum or maximum is going to be 0. That's the whole idea of the proof, right? That's what this picture says. Okay? And in order to say that, all I need to show is that the minimum... Why does it have a minimum and a maximum? Continuous on a closed interval, right? But maybe the minimum and the maximum are at the endpoints, in which case I can't use Fermat's theorem. So that's what I have to rule out, the possibility that the minimum and the maximum are at the endpoints. Okay? So proof. F is continuous on AB. Therefore, by, let's write Weierstrass 2, continuous function on a closed interval, by Weierstrass theorem, the second part, it has a minimum let's call it little m, and a maximum, let's call it big M.
Or it could be right.
And continuous function on a closed interval has a minimum and a maximum. And if it so happens that m equals m, that these values are equal, what does that mean? Right, it's a constant function. That's the only way that the maximum and the minimum can be the same. Do you agree? Then f equals some constant, right? In which case f prime of x equals 0 for all x. Do you agree? This we proved. If you take a constant function, its derivative is always 0. Do you agree? If m is not equal to m, so there could be two possibilities. Either little m is greater than big M, or little m is smaller than big M. But in fact, there's only one possibility, because if this is the minimum and this is the maximum, then the only other possibility is m is less than big M. Do you agree? If m is less than big M, this is the only other possibility, the statement is that they cannot both be obtained at the endpoints. Why? Right, because the values at the endpoints are equal. Do you agree? So if the minimum and the maximum are different, that's not going to work either. If the minimum and the maximum are different values, they can't both be obtained at the endpoints, because the values at the endpoints are the same. So at least one of them has to be at an inner point, either the minimum or the maximum. It could be that for example, that the endpoints are the maximum. If the function is, for example, like this, it could be that the maximum, that its maximum value is only at the endpoints. Do you see that? Think of a function like this. But then the minimum is going to be at an inner point. Okay, or vice versa. So let me write this a second. Then, at least one is not attained at an endpoint of the interval. And this is because, since f of a equals f of b. That's the assumption of the theorem. So the one that is not attained at the endpoint is, in fact, some point in, so call it C. So therefore, call it C. That C satisfies that what? It's a maxima and minima. The function is differentiable there. It's a maxima or a minima. It's inside the interval. The function is differentiable there. By Fermat's theorem, the derivative is 0. By Fermat. Questions on this theorem and its proof? Yes?
On the case, you were talking about a parabola, that it means that the maximum is going to be on the AB and the minimum is going to be at some point in the middle between them. On the case that on A and B you have a cos that is going to be not differentiable exactly.
I'm only looking at a function defined on the closed interval.
Defined, but it's not differentiable exactly
at the endpoints. I don't care. I don't care.
So we don't have to go
It doesn't. We don't require it. The only place No, 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 no. The only place that I'm using the fact that it's differentiable is to say if the maximum or minimum is inside the interval, and I argued to say that there must be one like that unless the function is constant, then I'm using this fact in order to use Fermat's theorem.
To understand that it's going to be a maximum and a minimum always.
That's a previous theorem. Weierstrass theorem told us, okay, so if you want to discuss the intuition in Weierstrass theorem again, let's do that over the break, not right now. But Weierstrass theorem told us, continuous function on a closed interval, nothing to do with differentiability, has a minimum and a maximum. That was Weierstrass. So this proof, I mean, if you think about it, if you read it again and think about it just a bit more, it's really just saying what this picture is saying. It's really just saying, okay, either the function is constant, in which case any point the derivative is 0, or it has to have a minimum or a maximum inside the interval, in which case the derivative is 0. Okay, this is really what this proof is saying. But this proof is not elementary at all. Because what's hidden here is, well, Fermat's theorem. Fermat's theorem is elementary. It just uses the definition of the derivative. But this is hidden here. The fact that the function must have a minimum and a maximum because of it's continuous on a closed interval because of Weierstrass. And proving Weierstrass part 2 stems from proving Weierstrass part 1, which uses Bolzano-Weierstrass in construction of subsequences that converge. I didn't show you that, but I said that's not trivial. And Bolzano-Weierstrass depends on this mysterious Cantor's lemma, which we mentioned a few times. So there's some real math going on in the background here. Okay? So, and that real math boils down to the definition of the limit for sequences, for functions. That's what it boils down to. And that kind of ties back to our discussion in the very first class of this semester, that just saying this is easy, why did it take so long to say this after that, and then say Lagrange, which we'll do after the break, and so on. Okay? Proving it, arguing it precisely, and thinking clearly in order to argue these things precisely, really waited, in some sense, for the precise definition of the limit, which was not available, for example, to Rolle, or to Lagrange, which followed. Let's have a break now, and we'll continue after the break.